Continuing with section 4.3, let's talk about linear independence. Here's the definition. A set of vectors in a vector space V is said to be linearly independent if no vector in that set can be expressed as a linear combination of the other vectors in the set. A set of vectors that are not linearly independent is said to be linearly dependent. Here's an example. Let S be the set consisting of these three vectors in R2. Is S linearly independent or is it linearly dependent? We've seen that the first two vectors listed, -1, 4 and -2, 2, they span R2. And so we should be able to express 3, 0 as a linear combination of these two vectors. And so this set should be linearly dependent. Now let's figure out how to express 3, 0 as a linear combination of these two vectors. Well, we've seen that you make the augmented matrix and then you row reduce it. And you get to this point here. This isn't completely in the reduced form, but it'll work. So we get that C2 is equal to -2. And this first row here says C1, or 1 times C1 plus 2 times C2 equals -3. And then substituting our known value of C2, we get that C1 equals 1. So therefore, the linear combination of -1, 4 and the other vector 2, 2 that gives rise to 3, 0 as a linear combination is 1 times this first vector plus -2 times the second vector. And indeed, once you do the arithmetic, you do indeed get that this equality holds. And therefore, the answer is that the set here is linearly dependent. We can express one of the vectors, namely 3, 0, as a linear combination of the others. The set consisting of just the first two vectors is linearly independent. You can't express the question of a set of vectors being linearly independent or dependent. You can't always just focus on the last vector listed and try to express it or see whether it can be expressed as some linear combination of the first few vectors. So let's try to find a reformulation to make the condition a little more symmetric. So notice that if we rewrite the equation we found on the previous slide, expressing 3, 0 as a linear combination of these two vectors, let's move the 3, 0 or subtract off the 3, 0 vector to this side, introducing a -1 coefficient. And then what we see is that we've got a linear combination of the three given vectors that adds up to the 0 vector. And this linear combination is something different than all coefficients being 0. That would certainly give the 0 vector. And this gives rise to a simple theorem that a non-empty set of vectors are linearly independent if the only numbers, k1 up to kr, that satisfy k1 times v1 plus k2 times v2 all the way up to kr times vr equaling 0 are the situations or numbers where their k1, k2, k3 are all 0 up to kr. This condition here, that the only linear combination of the vectors adding to 0 is the obvious one, where all the coefficients are 0, is actually sometimes given as a definition of linearly independent. That's because it's very convenient. You just have to check or begin with a single equation and find that this is the only solution. Let's do an example from page 210 of Anton, number 3. Determine if the given vectors are linearly independent in R4. So here are some 4 vectors that they've been given, and we have to determine if they're linearly independent or dependent. So what that entails is we have to begin with this equation here. Suppose there were some numbers k1, k2, k3, and k4 such that this linear combination equals to 0. Does that mean that these all have to be 0, or are there some others? And this type of question is what we've been addressing throughout the course, and we cook up a matrix and row reduce it. That's what I've done on this slide. I've made a matrix whose columns were the given vectors, and then we have this column vector consisting of the coefficients, and we want the product of these two matrices to equal to 0 matrix, or 0 column vector, and we have to row reduce this matrix to get this, and what we see is that, well, k4 can be anything, since it's a free variable. Then this equation here says k3 plus k4 is equal to 0, and so that allows us to express k3 in terms of k4. This equation here will allow us to solve for k2 as some linear combination of k3 if I haven't completely reduced this matrix, and so on. K1 will be a linear combination of k2 and k3 and k4, and so these vectors that were given to us were linearly dependent because there is a non-zero solution. Just take k4 to be something non-zero like 1, and then that will guarantee that no matter what these are, k1, k2, those might happen to be 0 depending on what these unspecified coefficients are. But because k4 is 1, we know that there is some non-zero solution, and therefore these vectors are linearly dependent. Let's try the same question for these four other vectors. In other words, are these 4 vectors in R4 linearly independent or linearly dependent? And we throw these into a matrix and row reduce it. Here I've done the sage math, and it turns out that the reduced row echelon form has 1s along the diagonals, and this implies that k1 is 0, k4 is 0, k3, k2, and all these are 0, and so these vectors are linearly independent. Now, a simple fact is if you have a set consisting of 2 vectors, they're linearly independent if and only if neither vector is a scalar multiple of the other.